Hello, Method 21 students. Welcome to the lesson about null space, column space, and row space. At the end, we're going to study about determinants as well. Part number 1, null space of A. From last day's lecture, everyone, we studied null space of A many times. Last time, we used a different word than null space, which is technically the same space, kernel of T, where the elements in the domain that map to the zero vector in the codomain. These vectors, x1, x2, x3, and so on, the set of these vectors that are mapped to the zero vector in the codomain is called the kernel of T. But if we don't talk about linear transformation, then these vectors, the solution set to the equation ax equal to 0, ax equal to 0 equation has a solution, x1, x2, and so on, right? And the collection of all solutions to the homogeneous equation forms the null space of A. So everyone, I don't have to teach you the new thing. This is kind of review from last time. How about we go to the example right away and find out the null space of A. Remember, finding the null space of A is exactly the same as finding the kernel of T from last day's lecture. If you want, you can go back to the last day's lecture and watch the kernel of T. You guys know that finding null space of A is the same as solving the equation ax equal to 0, which means the homogeneous equation, right? So, just like the previous lecture, we're going to start by solving the system. Okay, everyone. In order for us to find out the null space of A, we need to know what A is. In this case, the coefficient matrix is 1, 3, negative 2, 3, 0, negative 4, forms the matrix A. Now, we set up an augmented matrix with this A and the augmented column 0, 0, and solve the system by finding the reduced echelon form. Here you go, everyone. We have reduced echelon form of this augmented matrix. We have two pivots. And then we have one free variable. So, as a solution form, the third variable x3 is the free s1. x2 is equal to 2 over 9 s1. x1 is equal to 4 over 3 s1. And now we have the general solutions to this homogeneous equation, everyone. As you can see, we have infinitely many solutions, and we have a fraction coefficients, 4 over 3, 2 over 9, and 1. If you don't like fractions, like 4 over 3, 2 over 9, and so on, find out the lowest common multiple of 3 and 9, and then clear the denominator like this. Do you believe that the scalar times by 12 to 9 vector is equivalent to 4 over 3, 2 over 9, and 1 times by s1? This is equivalent to this one because I basically multiplied each fraction by the lowest common multiple, which is 9. So 1 times by 9 is 9. 2 over 9 times by 9 is 2. 4 over 3 times by 9 is 12, and so on. So, if you guys don't like the fractions, you're welcome to use these integers with the scalar s. Wait a minute, we have only one vector that spans the solution set of the system. Do you know what this means? It means this vector, this non-zero vector, forms a basis for the null space. Everyone, what is the dimension of the null space of A? The dimension means how many vectors do you see in the basis? In this case, we only have one. This means our new terminology, which is nullity of A, which basically means the dimension of the null space of A is 1. Thank you so much, everyone. This is the answer for the first example. Let's move on to the next page. Now you guys know the meaning of null space of A and the nullity of A. The next page shows the proper definition of these terminologies. Definition 4.2. Null space of A is written this way, NULL with a bracket A. This is basically nothing more than the set of solutions to the equation AX equal to 0. That's it. And then nullity of A is nothing more than the dimension of null space of A. That's it. So the nullity of A in the previous case was 1 because we have only one vector in the basis. If a basis for the space has more than one vectors, then just count the number of vectors in the basis. That's it. This question is also very easy because it's basically asking the same thing. Find the basis for the null space of A and find out the dimension of the null space of A, which means nullity of A. We have a good news. This matrix A is already in the descending staircase pattern. Do you know what this means? It means this matrix is already in an echelon form. Whenever you talk about null space of A, right? Null space means you try to solve the equation AX equal to 0. In matrix world, whenever you have equal sign here, then you can set up an augmented matrix. So let's set up an augmented matrix for this guy. You guys know that this augmented matrix is not in reduced echelon form. It's only in echelon form. Do you know why? Look at the pivot here. For this pivot column, these numbers must be 0, right? In order to talk about reduced echelon form. But because we don't have zeros going on, we need to convert this echelon form into reduced echelon form by performing two elementary operations. Very simple, two elementary operations. Let it begin. The reduced echelon form for this matrix becomes this becomes like this, and now you believe column 1, column 2, and column 4 are the pivot columns, and column 3 and column 5 are the free variable columns. So now you have two free variables, right? S1 here and S2 here. So our x5 equal to S2, x3 is equal to S1. Let it begin. Okay, everyone. This whole thing is the general solution to the equation AX equal to 0. So now the question is, how can we write this as a vector form? Once we write this as a vector form, we're going to end up having S1 times by one vector plus S2 times by another vector. We're going to find two vectors, right? Two vectors means the dimension of null space of A is 2. So first, let's find out a basis for null space of A. There you go, everyone. You can check that we have two vectors here, and these two vectors form a basis for the null space of A. you can easily check that these two vectors are linearly independent. Therefore, this set forms a basis for the null space of A, and because we have two vectors in the basis, the nullity of A is 2. Basically, everyone, the number of free variables in this augmented matrix tells you the number of vectors in the basis. Thank you. This is the end of null space A concepts. In part 2, we're going to talk about column space of A, which is technically the same as the range of T. Once we learn null space, column space, and row space, we're going to talk about a very beautiful theorem called rank nullity theorem in part 3. Okay, thank you very much, everyone. See you soon with part number 2. Part number 2, we study column space, row space of A. Just like the previous lesson, finding a basis is very important. Do you remember in the previous lesson, we learned how to find a basis using two different methods. Method 1, as normal, we use column vectors here, and then find out the echelon form. Once we find out the echelon form, we had to remember the pivot positions and copy and paste the original vector for that pivot position. That was the method 1. In fact, everyone, the first method we learned last time was the method to find a column space of A. Now, do you remember when we talked about the second method? For this second method, we had to transpose this original matrix and then find out the echelon form. In fact, this transpose method is the way to find the row space of A. So if you know how to do two different methods from last time, like this, then you know how to find out the column space of A, how to find out the row space of A. If you're confused how to do these two techniques, feel free to go back to the previous video and learn how to find a basis using two different methods. This time, we're going to go back to this slide again. The only difference between the previous lesson and this lesson is that I changed the letter subspace S to column space of A, and I changed the subspace S to row space of A. Please remember, these two spaces are different in a sense that column space of A is living in the codomain, row space of A is living in the domain. But anyways, the method is actually very similar. The key thing to remember is to perform elementary operations and get the echelon form. Remember, this was the echelon form of this original matrix A. Now the question is, how do we find out the column space of A? Column space of A can be found by looking at the pivot position. Since we have a pivot in the first column, you go back to the original matrix and copy and paste this original vector. Therefore, everyone, the column space of A is not just the span of two vectors, but it can be rewritten as span of one vector, in particular 2, -8. We only need this one vector instead of two vectors because one of them is garbage, in a sense that this vector is a scalar multiple of the other one. Do you know what this means? We have a linearly independent set here, and we have a minimum number of vectors to span the column space of A. This means we've successfully figured out the basis for a column space of A. Now look at the basis here. We only have one vector in it. This means the dimension of column space of A is equal to 1. Do you agree? Thank you very much, everyone. This is the method to find out the column space of A and its basis and its dimension. Shall we do exactly the same thing, except that we're using the transpose, and find out the row space of A? Let it begin. There you go, everyone. This is the echelon form of this matrix A. The only difference between the first method and then the second method is that the first method requires you to remember the pivot position, but the second method only requires you to scratch out the zero vector as a row, okay? And then copy and paste non-zero vectors as row. Because we only have one non-zero row vector, span of this vector gives us the row space of A. And remember, row space of A is a subspace of the domain. Column space of A is the subspace of the codomain. Surely, we only have one vector in the spanning set. Therefore, this is linearly independent, and we have a minimum number of vectors needed to span row space of A. Therefore, everyone, a basis for row space of A is basically this vector. Now, because we only have one vector in the set, the dimension of the row space of A is exactly equal to 1. Before we move on to the next page, I want to mention one more time that column space of A, row space of A, they don't need to be the same. We have same set here, but it's very rare coincidence that they have the same set for row space of A and column space of A. Quite often, it doesn't make sense that they are equal because one of them is a subspace of domain, the other one is a subspace of the codomain. But one thing that they are equal to each other is the number of pivots. The number of pivots are the same. Right here, right here. The dimension right here, and then the dimension right here. So could you please remember that the dimension, the number of pivots for each case is equal to each other, 1 and 1 here. Because they are equal to each other, we have a special name for dimension for column space of A, dimension of row space of A. We have a special name for this. It's called the rank of A. Thank you, everyone. I think we are ready to talk about the next example. We're going to do one example finding the column space of A and its basis. We're going to do one example finding row space of A and its basis. Let it begin. Here's the first example about column space of A. Given that we have a matrix A like this, the question is, find the column space of A without any calculations. Without any calculations means we don't care whether these four vectors are linearly independent or not. We don't care about having the minimum number of vectors. Just copy and paste these vectors which span the entire column space of A. So no calculation at all, just copy and paste. Isn't it so easy, everyone? This is all you have to do for part A. How about part B? Now we make this as a matrix and then find an echelon form. After finding the echelon form, we see that we have two pivots and two free variables. The only information we need is to remember or memorize the pivot positions in this echelon form. Column 1, column 2 are the pivot columns, right? Then these two vectors in the original matrix form a basis for the column space of A. Finally, everyone, what is the dimension of column space of A? It's 2. Because count the number of vectors in this basis for column space of A. Surely it's 2, isn't it? Thank you very much. This is the end of column space of A example. How about we perform the method 2 to find out row space of A? Once again, we're going to use exactly the same matrix A. Without any calculation, find the row space of A, everyone. Just like this previous case, row space of A can be found by spanning the 3 rows of the matrix. Without any calculations, we don't need to worry about whether these vectors are linearly independent, or we don't have to worry about the minimum number of vectors. So just copy and paste these vectors. Now you believe that row space of A is a subspace of R4. R4 means the domain if it's a transformation. Column space of A has 3 entries. In other words, column space of A is a subspace of the codomain if we define a transformation. We're going to form these vectors as a matrix and find echelon form. Okay, everyone. Now we have the matrix containing these vectors, which span the row space of A. In order for us to find out a basis for the row space of A, we actually have to find out the transpose of this matrix. But you know what? Surprisingly, the transpose of this matrix is exactly the same as A. So now we have actually the original matrix A. So this makes sense. This question makes sense where we have to find out the echelon form of A, which is basically copy and paste this matrix and find echelon form. For those of you who wants to save some time writing this matrix, you can just ignore this and copy and paste the original matrix and find the echelon form. Look, we found out the echelon form right here. Everyone, this is the echelon form of this matrix. Now you clearly see the last row is the 0 vector, so you cross it out. And you guys see that the first row and then the second row are the non-zero rows for this echelon form. Do you know what this means? It means the first 2 rows form a basis for the row space of A. There you go, everyone. Now, what is the dimension of the row space of A? I told you the dimension of column space of A, the dimension of the row space of A, they have to be equal to each other. There you go. This is the answer for this question here. Now, in the next page, I'm going to give you the proper definition of column space of A and row space of A. The column space of A is a subspace of the codomain spanned by the column vectors of A and is denoted by column space of A. You know what? When I say codomain, Rn means the number of rows for that matrix A. When we talk about row space of A, it's a subspace of Rm. When I say domain Rm, then this M corresponds to the number of columns of A. And we denote this space as a row of A, like row space of A. So just to summarize what we've done just now, for a column space of A, you have to remember the pivot positions and copy and paste the original vectors to find the basis for a column space of A. For the row space of A, you try to copy and paste the original matrix and find echelon form, and then cross out the zero vector as a row, and then you take the non-zero vectors as rows and form a basis for the subspace row space of A. So that's the clear difference between finding column space of A and row space of A. And this theorem summarizes what I just said. The actual column vectors of A corresponding to the pivot positions of its echelon form of A forms a basis for a column space of A. For part B, non-zero rows form a basis for the row space of A. So basically, theorem 4.20 is the summary of what we've learned just now. Thank you. This is the end of part 2. We're going to move on to part 3. And here we talk about rank and nullity. You know, nullity is the dimension of the null space. Rank is the dimension of the column space or dimension of the row space. If you add them up, then you get the total number of variables. It's like the number of pivot plus number of free variables becomes the total number of variables, just like week number 1. Thank you, and see you soon with part 3. Part number 3, rank and nullity of matrix A. Before, we talked about nullity, which is the dimension of the null space of A. Rank is the dimension of the column space of A. Or you can think of rank as the dimension of the row space of A. They are the same. So the next page shows what we've learned today. We learned today that the dimension of the column space equals the dimension of the row space, everyone. And at the same time, rank of A is called the dimension of the column or row space of A. What this means is that rank of A is equivalent to the dimension of column space or the dimension of the row space. Same thing. When we talk about rank is the number of pivots for this matrix. Nullity is the number of free variables for the matrix. So, in order to find out the number of pivots and number of free variables, what do you have to do? You just have to find an echelon form of this matrix. Everyone, the echelon form of this matrix A looks like this. We have 2 pivots in yellow highlighted portion. We have 3 free variables. This means we have 2 pivots and then 3 free variables. Number of pivots means the rank of A is 2. Number of free variables means the nullity of matrix A. So here's the answer. Now, did you also notice that the sum of rank of A, nullity of A, becomes the total number of columns? The total number of columns in week 1, we set the total number of variables. So the total number of variables is equal to the number of pivots plus the number of free variables. So rank of A plus nullity of A becomes the number of columns of A. This kind of result brings us one theorem called, this brings us one of the important theorems in this course called rank nullity theorem. if we have m number of columns, m is equal to the rank of A plus nullity of A, which means number of pivots plus number of free variables becomes the total number of columns. In the next page, we're going to use rank nullity theorem to solve one problem. Okay, everyone, let's tackle this question together. We have a matrix A that has 5 rows and 13 columns. Right away, this number 13 tells you the total number of variables. In other words, the m is equal to 13 from the rank nullity theorem. So this m is equal to 13. Now, how can we find out the nullity of A? The nullity of A is the dimension of the kernel space. The question said the dimension of the kernel of T is 9. That means our nullity in this case is 9. So now you have a feeling that if we use the rank nullity theorem, we can probably solve for the rank of A. But we know the nullity of A is 9, and then the total number of variables or the total number of columns we have is 13. Therefore, the rank of A is 13 take away 9 becomes 4. And you guys know that the rank of A is equivalent to the dimension of the column space of A. The dimension of the column space of A is exactly equal to the dimension of the range of T. Thank you. This is the end of the problem. Part number 4. We briefly discuss about a few results from this lesson. The first one is called existence and uniqueness. If B is in the column space of A, what this means is vector B is in the column space of A within codomain. Column space of A is also known as the range of T if you define a function. So everyone, it really makes sense that if a vector is living in the range of T, then there is a vector X in the domain such that it's sent to the vector B in the range. So the system AX equal to B is consistent, that meaning that you can find a vector X in the domain if and only if B is in the range of T. They're equivalent statements. Now, we could have multiple vectors mapped to the same vector B in the range of T. In that case, T is not one-to-one like this. Say we have another vector that maps the same vector B in the codomain. Surely, this kind of relationship is not one-to-one. Therefore, we cannot find a unique solution X such that AX equal to B. So in order for us to have uniqueness of solution, B must be in the column space of A, of course. In other words, pivot in every row. Also, the columns of the matrix A are linearly independent. In other words, pivot in every column. So altogether, pivot in every row, pivot in every column gives you a unique solution. You kind of know this from well in advance. Pivot in every row, pivot in every column lead us to one theorem for this course. It's called the big theorem. Pivot in every column and pivot in every row must have n by n matrix. which means the matrix A is n by n square matrix, right? Whenever we have pivot in every column, every row, think about the big theorem for this course. Look, everyone, if we have a pivot in every row, pivot in every row means it doesn't matter which vector you choose in the codomain, you will always find some x in the domain such that it maps to the particular b in the codomain. Did you just hear what I said? I said any member in the codomain can be mapped from some vectors in the domain. So in other words, the range of T is the entire codomain. We can say column space of A is equal to Rn. Now, because we have pivot in every row, column space of A equal to Rn for this special case also gives the row space of A equal to Rn as well. And you guys know they both have the same dimension n. I just said they both have the same dimension n. Same dimension means rank of A must be equal to n. So when you're dealing with a big theorem, where square matrix and T is 1 to 1 and on to, then we have a best possible situation to work with everything. Thank you. This is the end of part 4. In the next part, we're going to learn very fun concept called determinants. Determinants are very useful in matrix algebra world because determinant determines whether we have invertible matrices or not. In other words, whether we have a unique solution to an equation or not. So stay tuned, and we're going to have a very short video about determinants for warm-up. Section 5.1, Introduction to Determinants. Today, we're only going to do a warm-up questions. In week 11, we're going to learn more about determinants. Like I mentioned earlier, determinants determines whether a matrix A is invertible or not. So for fun, how about we use a quick formula to find inverse of A and try to find the concept of determinants. So like this. A times by D minus B times by C. And then you have to switch the numbers on the diagonal and then put the negative here, put the negative here. Here, 28 take away 6 is 22. Look at this, everyone. If you look at the denominator, 4 times by 7 minus 2 times by 3, you clearly see that the denominator is non-zero. Since the denominator is non-zero, we have some number at the bottom like this. Therefore, we can find out the inverse matrix, A. Now, take a look at this question here. We have 1 over 24 take away 24. Looking at the bottom, we see the denominator becomes 0. Therefore, this is not possible. In other words, this shortcut formula from before we actually learned something about determinant as well. The determinant in this case was staying at the bottom, AD minus BC as the denominator. This determinant determines whether we have inverse matrix or no inverse matrix. So here's the conclusion. If A is written 2 by 2 matrix with entries A, B, C, and D, then the determinant of A is written as AD minus BC. So as long as this determinant of A is non-zero, then that particular square matrix is invertible. Unfortunately, this formula works only for 2 by 2 matrix, okay? In the future weeks, we're gonna see more higher dimension matrices like 3 by 3, 4 by 4, and find their determinants. So for today, we're only going to learn this definition. Determinant of a 2 by 2 matrix, say we have A, B, C, D. The determinant of A is A times by D, which is this guy, minus B times by C, which is this guy. So in the future week, we're going to study more about determinants, especially with higher dimensional matrices. Thank you so much, everyone. This is the end of today's lecture. Have a great day.